Right. Hi, everyone. So we're very happy to continue with the theme of quasi-alternating links to have Khaled Qazaqzeh from Kuwait University, who is going to tell us about on the finiteness of quasi-alternating links. Khaled, please.
Thank you, Sham. Thank you very much. And I'd like to start by thanking the organizers, especially Sham and Aisha, for this invitation and this great conference. And allowing me to speak on the finiteness of quasi-alternating links. I know this is the same topic that Nafi did speak about. I will try my best not to have the same stuff again, but there are a lot of stuff in common between Nafi's talk and my talk, but I will do my best just to make it look different. So let me first outline my talk. So my talk will consist of the following parts. In the first section, I will just recall very quickly the definition of a quasi-alternating links that we have seen in Nafi's talk. In section number 2, I will be talking about some questions. And these questions basically is the main motivation of this work. In section 3, I will give the main theorem, and this main theorem will give a positive answer of one of the questions in section 2. And in that section, I will give also the proof of that main theorem. In section number 4, I will give some consequences of the main theorem. And after that, in section number 5, I will be talking about some examples and further discussion. And in the last section, I will be just listing some references for my talk. So let me go and recall the definition of a quasi-alternating links that were defined by Zavich and Szabo in 2005. Basically, they defined this class of links because this class of links share nice homological properties with the class of alternating links. We have seen too many properties in Nafi talk. I will try to not speak about these properties, but let me first just recall the definition very quickly. So how do we define the class of a quasi-alternating links? It's basically the smallest set of links that satisfy the following. Basically, the N naught has to be quasi-alternating. How do I know that a link is quasi-alternating? So if we have a link with a link diagram containing a cross and C, such that both smoothings of this link at this crossing that are named L0 and L1, as we see in this figure, if both of them belong to Q and both of them have determinant bigger than 1, and the determinant of the link L is additive at the cross and C, that means it is equal to the sum of the determinants of the two links L0 and L1, then in this case we say that L is in this set, so it is a quasi-alternating, and we say that it is a quasi-alternating at this specific crossing. Okay. So as we have seen in Nafi's talk, I mean, it's not too hard to see that any alternating link is actually a quasi-alternating, and it is actually a quasi-alternating. I need to just specify that we're talking about non-split alternating link. Is a quasi-alternating, and it is actually quasi-alternating at any reduced alternating diagram, at any crossing of any reduced alternating diagram. Therefore, we can consider quasi-alternating links to be a natural generalization of alternating links. This is basically the main motivation of this talk, is to try to generalize some of the known properties for alternating links to the class of quasi-alternating links. For these properties that I'm going to be discussing in my talk, I will need some facts or some known facts about alternating links that will be used to study these properties. So the first fact that we know about alternating links, that there are only finitely many alternating links of a cross number less than or equal to some positive integer. This is a very simple fact that follows since we know that, that there are only finitely many links of across a number less than or equal to some positive integer. The second, yes?
Generalize this, if you take the Skane relation, if you take the Skane relation for link homology, it's a exact sequence,
okay.
Right? Can you express quasi-alternating or alternating in terms of that exact sequence? Is there a way of expressing the conditions that define your quasi-alternating links in terms of statements about the Skane relation for homology? Because it seems like you're making a statement about crossings and comparing it to resolutions, correct? That was your definition?
Yes.
So it seems like that data should be recoverable using the Skane relation. Maybe it's too naive a question.
I think probably we should ask Zavich and Szabo about this question, but I mean, I agree with you. Probably this class of links probably somehow it is characterized in terms of L0 and L1. So, as you mentioned, that covariant homology can be obtained by the long exact sequence on L0 and L1. So somehow we might say that this long exact sequence might be, I mean, we might be able to use it to characterize somehow. But I don't know the answer if it is yes or no.
I ask because the previous talk, the last question was a topological characterization. And the Skane relation is a topological characterization. So that's
then we should ask Nafa if he... OK. Thank you for the question. OK. The second known fact that I'm going to be using, that the determinant of any alternating link is an upper bound of the Krausen number. This is basically true because we know that the determinant is in the case of alternating links, is equal to the number of spanning trees of any Tate graph of the corresponding alternating diagram. The third fact that probably Nafa did talk about, but he was using the span, but here I'm using the breadth. It means the same thing, that the breadth of the Jones polynomial of any alternating link is equal to the Krausen number of the given alternating link. So these basic facts will give me the following properties of alternating links. The first property says that there are, I mean, I would call them finiteness properties of alternating links because finiteness appear in every statement of the 4 properties. Probably you have noticed that. There are only finitely many alternating links of a given determinant. This basically follows from what we have seen in the known facts because the given determinant basically is a positive integer, and we know that there are only finitely many alternating links of across a number less than or equal any positive integer. In this case, that positive integer is the determinant. Also, we can say that there are only finitely many values of the Jones polynomial of alternating links of a given determinant. So for a given determinant, then you can find only finitely many values of the Jones polynomial. This is true because the given determinant, again, determines only finitely many alternating links of that determinant from the first sentence. So we get only finitely many values of the Jones polynomial in that case. In number 3, there are only finitely many alternating links of a given Jones polynomial. So if you fix the Jones polynomial and you ask how many alternating links of that Jones polynomial, we would have only finitely many. The reason, because the breadth of such Jones polynomial would be equal to the Krausen number of that alternating link, and we know there are only finitely many alternating links of that Krausen number. In property number 4, there are only finitely many alternating links of a given breadth of the Jones polynomial. Even if you fix the breadth of the Jones polynomial, then you would end up with only finitely many alternating links, again, because the breadth would represent the Krausen number, and we know that we have only finitely many alternating links of that Krausen number. So the question, can we generalize these finiteness properties to the class of quasi-alternating links? And for this end, I posted, this is just a proof for the facts that I mentioned, but trying to generalize these properties to the class of quasi-alternating links, I posted the following 4 questions, which, I mean, the first question is basically stating, is it true that there are only finitely many quasi-alternating links of a given determinant? Can we generalize the first property to this class of quasi-alternating links? The second question, is it true that there are only finitely many values of the Jones polynomial of quasi-alternating links of a given determinant? Question number 3, is it true that there are only finitely many quasi-alternating links of a given Jones polynomial? And number 4, is it true that there are only finitely many quasi-alternating links of a given breadth of the Jones polynomial? So basically, in these 4 questions, we are asking, can we generalize the 4 properties that are known for alternating links to the class of quasi-alternating links? Before we go into discussing these questions, I would like just to state 2 conjectures that have that have something to do with these questions. The first conjecture, which is due to Green in 2010, which basically states that there are only finitely many quasi-alternating links of a given determinant. If we can establish this conjecture, that right away would give us a positive answer to the first question. And actually, if we think deeper, this also would give us a positive solution for second and the third questions that I have listed. And trying to establish this conjecture in 2013 in a joint work with Koplan and Jaradat, we proposed the following conjecture, which states that for any quasi-alternating link, we have the Crossen number less than or equal to the determinant. This conjecture actually, first of all, it implies, I mean, if it holds, then it would imply, it would establish Green's conjecture. It would give a nice property for quasi-alternating links, which is a natural generalization of one of the known facts about alternating links. And it will give a very nice abstraction for the link to be quasi-alternating, because it is given in terms of the Crossen number and the determinant. Okay, what do we know about these conjectures? As probably Nafi' mentioned in his talk, that for Green's conjecture, there is some work by different people that they proved that Green's conjecture holds for all quasi-alternating links of determinant less than or equal to 7. For the other conjecture, we verified it for infinitely many quasi-alternating links and for all quasi-alternating links that are known till now in the literature. But we don't know if it holds or if we have a counterexample for that. Now let me go to the main theorem of this talk, which in this theorem I'm trying to give a positive answer to one of the 4 questions I posted, which is question number 2. So I will try to give, the main theorem gives a positive solution for question number 2 without any assumption about the conjectures that we have seen about Green's conjecture or our conjecture. So the main theorem says that there are only finitely many values of the Jones polynomial of quasi-alternating links of a given determinant. So this theorem gives a positive solution for the second question with no assumption. I would like to say something about the proof of this theorem, but before I go into the proof, let me just recall a few definitions and results from Nafi's talk before we go into the proof. So first of all, I want to recall the definition of the Jones polynomial. Probably in Nafi's talk, he used the Skene relation for the Jones polynomial, but here I will just use the Kaufman bracket to define the Jones polynomial. So the Jones polynomial of an oriented link is the Laurent polynomial in t to power plus minus a half with integer coefficients that is defined by minus a to power minus 3 times the right times the Kaufman bracket of the link L, where we do the evaluation t to power a half equal to a to power minus 2. The right, probably you know what is the right is, but just to recall that the right is the difference between the number of positive crossings and the number of negative crossings, where a crossing that looks like this is called a positive crossing, and a crossing that looks like this is called a negative crossing in the oriented link diagram of L. It's not too hard to show the following lemma, which gives the Jones polynomial of any link at the cross and C in terms of the Jones polynomial of the two smoothings, L0 and L1, according to one of the following two skew relations. But I want to say that this is up to mirror image, so I'm working up to a mirror image. If we consider that without up to a mirror image, then we would have 4 cases. But up to a mirror image, we have only 2 skew relations for the Jones polynomial of the link L at the cross and C in terms of the Jones polynomial of the links L0 and L1. If you've noticed in these two formulas, I mean, in the first formula, this is where when the crossing is positive, but in the second formula, we use it when C is a negative crossing. In both formulas, there is the number E. Number E represents is the difference between the number of negative crossings in the link L1 and the original link L. Here I'm talking about oriented links. Also, for the proof, I needed the following lemma, which says that the absolute value of any coefficient of any quasi-alternating link is bounded above by the determinant. So in the case of quasi-alternating links, we know an upper bound and a lower bound for the coefficients of the Jones polynomial in that case. Okay. Also, I would like to recall the definition of the gap that was introduced in Nafi's talk, that we say that a polynomial has a gap of length s if this polynomial has two monomials of degree I and I plus s plus 1 of non-zero coefficients, and all the monomials with degree m have zero coefficients with m between I plus 1 all the way to I plus s. A result that is also mentioned by Nafi's talk, that if we were able to prove in a joint work with Nafi that if you have a quasi-alternating length, then the length of any gap in the Jones polynomial of that quasi-alternating length is 1. So we cannot have gaps bigger than 1 in the Jones polynomial of any quasi-alternating length. Last thing before I go into the proof and to sit at for the proof and for what's going to come later, we would like to define an equivalence relation in the class of quasi-alternating lengths, which is defined by setting two quasi-alternating lengths to be equal if they have the same link invariant, using that invariant. So we can define this equivalence relation on the class of quasi-alternating links for any link invariant. Namely, I will be using this equivalence relation for the Jones polynomial, for the determinant, for the breadth of the Jones polynomial, but you can define it for any link invariant, actually. So let me go on the proof. So as Nafi mentioned, most of the proofs in the class of quasi-alternating links works by induction on the determinant. So if we start with the determinant equal to 1, we know that there is only one quasi-alternating link of determinant 1, which is the n naught. And we know that we have only one value for the Jones polynomial in that case, so the result holds. Now, we assume that the result holds for all quasi-alternating links of determinant less than or equal to n. In particular, I can say that there is a finite list of quasi-alternating links, K1, K2, all the way to KL, of Jones polynomial equivalency classes. This is where I use the equivalency class I just defined. So we have a finite list of quasi-alternating links such that the Jones polynomial of any quasi-alternating link of determinant less than equal to n has to be equal to the Jones polynomial of one of these quasi-alternating links in this list. So this is what I'm trying to say. Now, if we go to any quasi-alternating link of determinant n plus 1, and from the definition of being a quasi-alternating, that means both smoothings, L0 and L1, would have determinant less than n plus 1. So by the induction hypothesis, the result holds for the links L0 and L1. What I mean by the induction hypothesis holds in this case that the Jones polynomial of the link L0 and the Jones polynomial of L1 would have values in the would be values equal to the Jones polynomial of one of the quasi-alternating links in this list. So we have only finitely many values for the Jones polynomial of the links L0 and L1. Now, before I go into the two cases of the proof, because I have two types of crossings, either positive or negative, I want just to let small m to be the minimum of the minimum degrees of all the Jones polynomial of the quasi-alternating links of all the quasi-alternating links ki, where I is between 1 and L, which is in the list that I have started with. And capital M is the maximum of all the maximum degrees of all the quasi-alternating links in the list K1 all the way to K sub L. Now, if we, in the first case, when the crossing is positive, then we know that the Jones polynomial of the quasi-alternating link L would be equal, using the skein relation that we have seen in the lemma, would be equal to this. Now we have finitely many values for the Jones polynomial of the link L0. We have finitely many values for the link, for the quasi-alternating link L1. And we must have only finitely many values for the number E, which represents the difference between the number of negative crossings in L1 and in L. Why is that? Because if we allow infinitely many values for E, that would force this polynomial to have gaps of lengths bigger than 1, which is not acceptable because we know that any gap in the Jones polynomial of any quasi-alternating link has to have length 1. So we have finitely many values here, finitely many values here. We have finitely many values for the number E. So we would have finitely many values for the whole polynomial, especially that we know that the minimum degree of this polynomial is bigger than or equal to this number, and the maximum degree has to be less than or equal to this number. So we have only finitely many choices for the coefficients of this polynomial and finitely many choices for the minimum and the maximum degree. So it has to be finite. This is the first case. The second case, we do just similar argument, but the difference is we just use the second skein relation. That's when the crossing is negative. Otherwise, the rest of the details will be the same. So let me just skip that to go to some consequences of this main theorem. So some applications of this main theorem lies in the first one in the following corollary, which says that there are only finitely many Jones polynomial equivalence classes of quasi-alternating links of determinant less than or equal to any positive integer. So if you fix a positive integer, then you would have only finitely many Jones polynomial equivalency classes of quasi-alternating links. And moreover, we can say something about even covanef homology equivalency classes, that there would be only finitely many covanef homology equivalency classes of quasi-alternating links of determinant less than or equal any positive integer. The proof of the first part follows directly actually from the main theorem, because we know that there are finitely many Jones polynomial equivalency classes of a given determinant. This is basically the main theorem. Now, if we allow, if we go to some positive integer, we would have only finitely many positive integer less than or equal to that determinant. That means we have only finitely many Jones polynomial equivalency classes. The second result follows directly because we know that the degraded Euler characteristic of the covariant homology is equal to the normalized Jones polynomial. Okay. Now one might wonder if these we have finitely many Jones polynomial equivalency classes, but one might wonder whether or not these equivalency classes are finite. So we might ask ourselves about the cardinality of these equivalency classes. We know that their number is finite, but what is the cardinality of each equivalency class? If we look at some examples, for example, if we look at the equivalency class, Jones polynomial equivalency class of 1. So if we ask ourselves how many quasi-alternating links of Jones polynomial equal to 1, we know that this is only the n0. So in this case, we know that the Jones polynomial equivalency class is finite. If we take any one of these Laurent polynomials, which does represent one of the Jones polynomial of one of the links or of one of the knots or link, of determinant 1 to 7, we can say the same thing, that any polynomial listed in this slide represents Jones polynomial equivalency class that is finite, because we know that there are only finitely many quasi-alternating lengths of determinant less than or equal to 7. Can we generalize this to any determinant? We don't know the answer because Green's conjecture, we don't know if it is true or not for determinant bigger than 7. But if we can prove it, then this would be the case. Based on this, another corollary which states the following: in the class of quasi-alternating lengths, one might start wondering about determinant equivalency classes and Jones polynomial equivalency classes. And this corollary says that every determinant equivalency class is finite, if and only if every Jones polynomial equivalency class is finite. So in the previous slide, and here, we did see that some of the Jones polynomial equivalency classes are finite, and we start wondering if this is going to be happening for all Jones polynomial equivalency classes. Well, we can say something in terms of the determinant. Well, this has something to do with the Green's conjecture. I will say something about this in a minute after we finish this corollary. So this corollary says the determinant equivalency classes are finite if and only if the Jones polynomial equivalency classes are finite. Well, if we try to prove this, I mean, the first implication follows directly because from the fact that the Jones polynomial equivalency classes consist of lengths of the same determinant. Any Jones polynomial equivalency class contains lengths of the same determinant. The second implication follows from the main theorem, since each determinant equivalency class would be a finite union of Jones polynomial equivalency classes. So this is where we use the main theorem and the second implication. The first implication has nothing to do with the main theorem, but the second implication, this is where we use that we have only finitely many values of the Jones polynomial of a given determinant. Based on this corollary, we can restate Green's theorem, not in terms of determinant, in terms of the Jones polynomial. So Green's conjecture can be restated as follows, that there are only finitely many quasi-alternating lengths of a given Jones polynomial. So I don't know if this is going to make it easier, but anyway, this is equivalent to the main conjectures of a Green. Okay, another corollary We can also, based on this result, based on the main theorem, we can give the following corollary, which says in the class of quasi-alternating links, every breadth of the Jones polynomial equivalency class is finite, implies every determinant equivalency class is finite. This is, it's not too hard to see that the determinant equivalency class is a finite union of the breadth of the Jones polynomial equivalency classes as a result of the fact that the breadth of the Jones polynomial is bounded above by twice of the determinant. So based on the lemma that we have seen and Nafa did talk about, that the Jones polynomial of any quasi-alternating link, if it has a gap, then the gap would be at most of length 1. That would imply, actually, that the breadth is bounded above by twice of the determinant, at least, at most. Based on that, we can conclude this corollary. Now, one might wonder whether these questions will have positive or negative answer in the class of all links. So we did at least see that question number, I think 2 or 3. Let me just make sure. So based on our main theorem, which is this theorem, we give a positive answer to question number 2. But now, what about these questions in the class of all links? What can we say about the answer of these questions in the class of all links? Well, let me give you some examples that show that these questions will have negative answer in the class of all links. That's why these questions somehow are interesting in the class of quasi-alternating links, because they're not, they have negative answers in the class of all links, but they have positive answers in the class of alternating links. So we are in between. That's why it's very natural to ask whether these questions will have positive or negative answer. Anyway, let me look at some examples. So Kaninibu defined an, So Kaninibu defined an infinite family of knots that are given in terms of two integers, p and q. And in this family, all the members of this family of knots would have the same determinant, which is 25. And the Jones polynomial of every member of this family is given by, the Jones polynomial of every member of this family is given by this formula. So we see that the value of the Jones polynomial depends on just the sum of p and q, the sum of p and q. From this example, we can say that we can see that the main result doesn't hold in the class of all lengths, because this is an infinite family of knots with the same determinant, but with infinite values of the Jones polynomial. So the main theorem of this talk doesn't hold in the class of all lengths. And in addition to that, we can also see that the question number 1 and question number 2 have negative answers in the class of all lengths. Okay, another example. Yes, sure.
So do we know that there are finitely many Kaninibu knots which are quasi-alternating inside this family?
Yes. Okay.
Do we already know which ones are quasi-alternating, or are they?
Okay, good question, because the main theorem says that we have only finitely many values of the Jones polynomial. But can we, there are finitely many quasi-alternating lengths of a given determinant. This family consists of infinite family of knots of the same determinant. But we have infinitely many values for the Jones polynomial. So, you can say, you cannot conclude that there are only finitely many Kaninibu knots. We know this result, but not using this abstraction, using another abstraction. But using the main theorem, we cannot conclude that there are only finitely many Kaninibu knots that are quasi-alternating, because there are infinitely many Cannibu knots that share the same Jones polynomial because the Jones polynomial depends on the value, on the sum of P and Q. So if P plus Q is the same, then you can have infinitely many Cannibu knots of the same determinant with only one value of the Jones polynomial. These might be all quasi-alternating. We don't know. Okay? Okay. If we take a subfamily of this family, K of P comma Q, where P is positive and Q is negative, and we fix P plus Q. This family consists of knots of the same Jones polynomial. This is what I have been saying in the previous slide. And it's not too hard to see that all the members in this subfamily have different Crossen number. So we have infinite family of knots of the same Jones polynomial with different Crossen number. This implies that question number 3 has a negative answer. Because in question number 3, we ask whether we have infinitely, is there finitely many quasi-alternating links of given Jones polynomial. In the class of all links, this question has a negative answer based on this example. Okay. Another example, if we take another subfamily with P bigger than Q, bigger than 0, Q less than 0, and we fix in the absolute value of P plus Q to be less than or equal to 4, then all the members of this subfamily would have the same consist of knots of breadth 8. They have the same, they share the same breadth, which is equal to 8. And we can tell that they have different Crossen number because their the Crossen number of every member is going to be given by this formula. And that's why we can conclude that the question number 4 will have a negative answer in the class of all links. Now, one might wonder, I mean, is this the only family that gives counterexample or negative answer to the 4 questions? No, we can generalize this actually using this corollary based on the main theorem, which says if you have a link and the two smoothings of this link have non-zero Jones polynomial, and the determinant of L1 or the determinant of L0 is equal to 0, then we can construct an infinite family of links with the same determinant. And according to the main theorem, we can say that this family, or this family, depends on which case we're talking, whether the determinant of L1 equals 0 or the determinant of L0 equal to 0. This or this family will consist of, will contains only finitely many quasi-alternating links, and it will give us another example of a family of links that give us negative answers, at least for the first question. I mean, we can think deeper and go in the technical details, but just for the sake of timing, I will just skip the proof. So, I mean, basically the proof is these two families will have the same determinant because the determinant of L0 or L1 would be equal to 0. And the Jones polynomial of all the members of this family will have, I mean, distinct Jones polynomial according to the skein relations that we had in one of the lemmas. That's why we would have only finitely many links in this family of that would be quasi-alternating. Okay. So we have talked about the first 3 questions probably in more details, but I haven't talked too much about the 4th question. So I want to just include the last part just to try to give some idea about the answer of the 4th question. So this lemma, which basically states that if you have a quasi-alternating link of breadth less than or equal to 3, then we can easily prove by doing induction on the determinant of the link L that this knot or link has to be either the N knot or the half link or the trefoil knot. somehow, if you can generalize this idea, then we can give a positive answer for the fourth question. But this is only works till with the breadth less than or equal to 3. I mean, I'm not going to go in the technical details of the induction, but basically, let me just skip the first part and go to the second part of the proof. So according to the Skene relation that computes the Jones polynomial of the link L in terms of the Jones polynomial of L0 and L1, we know there is no cancellation in this Skene relation. And we know, yes, there is no cancellation. So for the link L, for the Jones polynomial of the link L to have breadth less than or equal to 3, that would force the breadth of the links L0 and L1 to have breadth less than or equal to 3, and with extra conditions on the monomials that appear in these two polynomials. That is where we use induction on the links L0 and L1, that either the L0 or L1 is the unknot or the half link, or the unknot or the half link or the trefoil. But in that case, that's using the sum formula for the determinant, if this is one of the three links, which are either the unknot or the half link or the trefoil, and the same thing for the link L1, then the determinant of this link has to be less than or equal to 6. But we know all the quasi-alternating lengths of determinant less than or equal to 6. And among these quasi-alternating lengths, there would be only 3 lengths with breadth less than or equal to 3, which is the unknot, the half link, or the trefoil, and that's it. For the last part of, or for the last slide of my talk, I would like just to close this talk with the following conjecture, which I'm proposing, that there are only finitely many quasi-alternating lengths of a given breadth of the Jones polynomial. Actually, this conjecture would imply, I mean, if we can establish this conjecture, this would imply Green's conjecture, and at the same time, it would give positive answer to all 4 questions. Thank you very much. This is a list of my references.
Any further questions for Khaled? So for this conjecture, is it one? I mean, is it iterative, or is it one shot? You think that you can address this? Would you need to enumerate them? Or?
I mean, the problem is, I mean, if we go back to this slide, I mean, we were able, I mean, at least we did verify. I mean, this lemma, this one, it does verify this conjecture when the breadth is less than or equal to 3. This is basically I mean, we are basically using the idea that the determinant of any quasi-alternating less than or equal to 6 has to be one of the, I mean, all the quasi-alternating lengths of determinant less than or equal to 6 are already known.
I see.
I mean, if we want to generalize this proof, then we need to specify all quasi-alternating lengths up to a given determinant, which is basically, that's Green's conjecture, that is there a finitely many quasi-alternating lengths of a given determinant or not.
Very good, thank you, sounds good. Yeah.
Yes, no.
One question for the last conjecture.
Yes.
So here, you know that the breadth of the Jones polynomial is less than the Corsing number, right?
Yes.
And the difference is, you can estimate this by the Toraev genus? There's a relation.
I have no idea. I don't know if...
I think the Toraev genus is bounded by the difference between these two times.
Okay, but I mean, are you suggesting that...
you can look at that, I don't know.
Okay,
maybe
thank you.
It can help.
But do you have any control of the Toraev genus of quasi-alternating lengths?
I don't know, but...
Okay.
Because for alternating, it's 0, right? For alternating,
yes, for alternating, yes.
But maybe, I
yes.
don't know.
Yes.
Since it is a quasi-alternating, we...
Yes. Thank you for the idea. Yes.
Okay, great. Any other questions? Okay, let's thank Khaled again for the...
Thank you very much.
Thank you.